So in the present video, I will be just summarizing the basic concepts of discrete combinatorial probability, how I typically think of it in my own mind, and maybe do a few problems from the book Zinfeng Zhao, named A Practical Guide to Quantitative Finance Interviews. So I will first start with a few definitions just to summarize everything. So the first definition is that of an outcome. We typically denote it by a small omega, and a set of all outcomes is called the sample space, which is denoted by capital omega, and this is our outcome. So just as an example, say we take the event of, or say we take a trial, which is something which yields various outcomes to us. A trial is the one which yields various omegas to us. Say our trial is a coin flip, and we are intending to flip up an unbiased, or let us just say a coin some number of times, or say I coin flip one time once. So what can my small omegas be? Say H denotes heads and T denotes tails, so my small omega can either be H or T, and this is an exhaustive thing, there cannot be anything else. So our capital omega, which was our sample space, will simply be a set of H comma T. So this was the first thing I wanted to mention. The second thing which we will see is what is meant by an event, and this definition is also closely linked to the idea of a sample space. So an event is basically a subset of a sample space. We typically denote it through capital letters like A, B, and so on, and it is a subset, might be proper subset as well, of the sample space omega. For example, if we consider a dice, rolling a dice, so say this is our dice and we intend to roll it, then there, what is our omega? Omega, capital omega, the sample space, it can be 1, 2, 6. This is the sample space we are operating in. Now say A, our event is that we get an even number out of the roll of the dice. So what is A? What are the outcomes belonging to A? What are the outcomes or the omegas, small omegas belonging to A? So A, if it is even, it might have 2, it will have rather 2, 4, and 6. And so we see that A is a proper subset of omega. So this is what is meant by an event. So we call A an event, the event of getting an even number when we roll a dice once. Okay, so now maybe we will move ahead. Okay, let me figure out a way to increase the size. Yes, maybe, yeah. So next we will move on to something called an indicator variable, because that is crucial, especially for the problems involving expected probabilities and so on. So let me reset it. Okay, fine. So for those problems we have something called an indicator variable I, This is usually used in problems involving expected value. So we will come to it, but for the moment you can consider it as something which indicates something about an outcome. So let us say we consider again the case where we roll a die. So associated with each outcome, basically I, the indicator variable, it maps an outcome to some number, and in this case the number is 1 or 0. 1 typically denotes plus or yes, or we are positive about it, and 0 denotes something which we are negative about. So say we consider the event of getting say an outcome 2. So, and the event is the same, right? Getting an even number. So 2 is an even number, so the indicator variable corresponding to this would be 1. So 2 gets mapped to 1 under I. Similarly, 1 would get matched to 0 because it is not an even number, but 4 again would get matched to 1, and so on. So this is an indicator variable. We will see its usage later on when we do some problems on it. And the indicator variable is a part of a class of larger set of variables which are called random variables. So indicator variable is a type of random variable. So so consider the random variable. What is a random variable? It is some x which maps each omega to some real number. So you can see indicator variable is also a type of random variable, just that the you can say the set of images of all omegas in X is just 1 and 0. So the random variable, typically random variables are again useful in problems involving expected values, and we will come to them as and when the time arrives. The idea is just to provide a brief summary of all the terms so that everybody is on the same page. So next, let us come to these are all, by the way, just reviews, just very quick reviews about the probability theory, because I am more interested in doing problems on this, because I don't think so. If somebody feels that they are not getting this in one go, they should look at some probability text, but my focus is mostly on problems, and just to provide a brief review of how I think of these topics, if that is relevant. So so next we come to something involving combinatorics. Combinatorics is just counting. Whenever we count something, that qualifies as a combinatorial thing. So for example, say you need to count the number, so you have say n objects, right? So in how many ways, and say they are all distinct, so you can differentiate them in some manner. So in how many ways can you arrange these n objects in n spaces, let us say, and they are all distinct? So this just involves the multiplication rule of probability, that for the first blank you can fill it in n ways, right? Now, corresponding to each one of the ways in which you have filled the first blank, the second blank can be filled in n-1 ways, because one of the objects has already been placed here, and so on. So basically the last one can be filled only in one way, because only one object would be left at that point. So just using the multiplication rule, again, if you are not familiar with these, you may refer to some standard probability text. My idea here is to solve more problems than to provide the basic review, because I feel these are the essential bits and require fundamental understanding of this. So basically now the number of ways you can arrange these n objects is simply n times n-1 and then so on up till 1. And this is commonly denoted as n factorial. So the number of ways to arrange n distinct objects on a straight line is simply n factorial. Next, maybe I will move on to definitions of combinations and permutations and how to intuitively reach those definitions. So what is a permutation? So you have n objects, and you have an object, say, and say you have to pick r of them, right? Pick r of them, and order matters basically. So in which order you pick them, that matters. So how many ways are there to arrange them? So that is commonly denoted as a permutation, NPR. But one thing I would like to remark about is that I personally don't tend to use NPR, because almost all the problems which require permutations are intuitive, and you can solve them using a parallel definition of a combination, which we will get to next, which is NCR. So mostly I think NCR definition is the one which I will stick with while solving problems. You can have your own conventions, that doesn't matter, but there is one special case where NPR definition is relevant, and that I think is something which is good to see. So just consider the case. This is interesting one actually. Just consider the case where you have n objects, right? Out of which A1 are of one kind. Say they are all, say, black maybe, right? And say A2 of them are blue, and so on, and say AK of them have some kth color, right? So now in how many ways can you arrange them? So let me first tell you the answer, and then maybe we will go on to explore why that is the case. The answer, the number of ways to arrange them, and this is very, very intuitive. If you look at this, you will get this very quickly. It is simply n factorial over the multiplication of ai factorial. So basically, or if you are not too comfortable with the pi notation, so it is basically simply n factorial upon a1 factorial and so on up to ak factorial. So why is this the case? So how I like to think of it, there are of course multiple ways to derive this result. How I like to think of it is that we have n objects, right? So just make n placeholders. And just use the concept of permutation. Just forget that they are alike of one kind, right? Assume they are all distinct. So the number of ways in which we could arrange them are n factorial, right? So this just follows from here, right? So now there are n factorial ways in which I have arranged all of them, but now say this one, and say this placeholder, and say this placeholder, they have something in common. Say they are all black, right? So what do we need to do? We basically the total number of ways just gets reduced by the number of times we can permute these among themselves. So basically in this case 3 factorial, because what we have done in the initial placement is that we have assumed them to be distinct. Let us call them, this is black of 1 kind, this is the black of 2 kind, this is the black of 3 kind. This is what has went on when we quote the answer as n factorial. We assume all of them are distinct. But now if they are all black, what we can do is just say that because what are the additional cases we are counting? We are counting the case B1, B2, B3, but it is equivalent to the case B1, B3, B2, right, which is again equivalent to the case B2, B1, B3, which is again equivalent to the case B2, B3, B1, which is again, and so on. So basically there are 3 factorial cases, that is 6 cases, which are getting overcounted, and for each one of these, right, we are getting all the possible combinations of these. So what we need to do eventually, the total number has to be reduced by the number of ways in which this B1, B2, B3 and so on can be permuted among themselves, right? So if the total number of ways is n factorial, we just need for this particular choice of black, which happens to repeat 3 times, we just have to divide the total number of cases by 3 factorial, which is the number of times black has appeared, and so on. And this has to go on for all the colors, and hence say up to AK, which can succinctly be denoted in this notation of pi. So this is an interesting case which will very intuitively lead to the definition of combinations as well. So let me try and erase all this, and then maybe we can go to the definition of combinations. So combination is just the number of ways given n objects. How many ways can you pick from n objects, and how many ways can you pick r objects? The order doesn't matter. Which object is picked first, it is of no consequence to us. I will also show how you can reach the definition of NPR very easily from NCR. So that is one other thing. Typically it is very closely linked. So let me just finish erasing all this. There should have been some method to erase it quickly, maybe, I don't know. Yeah. Oh my god. We will figure out. Okay, so yes, so now we have given n objects. Oops. Just set it to maybe 10. Yeah, given n objects, we need to select r of those. So what are we essentially doing? And so the number of ways to do this, it is denoted as NCR. Now what will be the value of NCR? So this also has a very intuitive explanation if you got the previous concept right. So if there are n objects with us, we have to select R. Say what we instead do is that we randomly take any permutation of this, right? Any valid permutation of this, and then we just pick the first R of these. We just select the first R of these. So what will be the number of ways in which we will be picking it. So basically there are n factorial ways in which we arrange all the n objects, and out of those n factorial ways we can just pick we can just pick the first r, right? So you may call it one selection, but the issue is that we might have a case where we pick 1, 2, 3, 4, 5, 6 and say 2, 1, 3, 4, 5, 6, and we are essentially picking the same numbers, right? But we are counting it as two different orderings here. So here what we instead will do, just as we did in the last case, is that we will say R are alike of one kind, right, of the first kind, and these are in some manner again alike because they are all not chosen. So what order comes in here also doesn't matter. What matters is that they are not chosen. So n minus r are alike of another kind. So what will be the number of ways to do this? It will, again, using the previous example, it will simply be n factorial upon r factorial into n minus r factorial, and this is the definition of NCR. And now how do you reach from NCR to NPR? What was NPR? It was just that the order does matter here, and what has not been chosen is irrelevant to us. So we just have n factorial upon r factorial of one kind, and all others can be ignored. So here we have NPR, here we have NCR. So that is why I said that you do not really need to know what NPR is, and essentially all the problems can be solved using NCR. N minus r factorial. So all the problems can be solved using NCR just by permuting your selection. So you have already selected r objects using the combination, and then you just permute them. Basically just take all possible ways to arrange them, and you will reach NPR. So there are other further useful properties of NCR and NPR, but I think one does not need to know that. As long as you know this definition, you can always derive those properties fairly easily. So I would not spend time discussing those properties. The last thing which is a famous counting technique is the principle of inclusion and exclusion, and with that I will conclude the video. I will again give an intuitive way of thinking about PIE, principle of inclusion-exclusion, which you might find useful, and in the further videos I will solve some problems on these topics and move to advanced topics like expected value and Bayes theorem and so on in probability. That is the larger plan. So in the principle of inclusion and exclusion, which just to save time I will simply write as pi, is that so the most intuitive way to think of this is through Venn diagrams, which I personally find really useful. Let us say you have this Venn diagram, right, and 3 case Venn diagrams are typically as farther as you can get, because 4 cases you cannot do by hand. Basically there is some formula for the same, but not here. And let me so the basic set theoretic notation that n of a Okay, let us just mark the zone. Say there is a number in this region, right? I should use something else, right? Some other color maybe. So let us use blue here. So this is our A region. Let us say this is our B region, and so on, right? Now you get the idea what I meant by the regions. So each of these, let us say this is C, D, E, F and G. So what is NA? NA will simply be the number of elements in A will simply be A plus B plus C. What is NB? Well, NB is simply C plus E plus F. And what is NC? NC is simply F plus G plus B. So say you need number of elements in A or B or C, which is the union. What is it? It is simply A plus B plus C plus D plus E plus F. So basically you can write it as number of elements in A plus number of elements in B plus number of elements in C. But you see that so for example, A includes C and B also includes C, so C gets counted twice when we do this thing. So what we need to do is maybe we should subtract A intersection B, and similarly B intersection C, and C intersection minus C intersection A, right? But now what happens? The central region was added thrice here, right? And it has been subtracted thrice. By the central region I mean this region. It was added thrice and subtracted thrice, so to count it at least once you just need to add it back to the result, that is A intersection B intersection C. And this is what is inclusion and exclusion for 3 sets. So now I will just list the final formula when we have an arbitrary number of sets, and that is where we will conclude this video. So from the next time onwards I will figure out some faster way to clear all this, because I think this, okay, what does delete do? Yeah, this is also good enough. Yeah, so anyway, the title wasn't needed. So yes, so to list the final form of PIE we need the union of several AIs, right? What is their union? You are given multiple AI events. How to find the probability of at least one happens, right? So that is denoted by this. This is basically, first of all, you take all n AIs and you sum them up, right? Then you subtract from it all the double intersections, and then you add to it triple ones, and till here, oh my god, IJK, yeah. Till here we had seen in the 3 case, but this can go on and on. Basically we will have to go up till all of the AIs, say it is up to K, so all the K's have been used up. So think this should be, just continue this sequence intersection of all AIs, and this just concludes. We will see how it is applied in problems, and that should provide you with an idea. So to sum up, this is just the fastest introduction. I think it took half an hour, but I think the fastest possible introduction for those who are already familiar with the subject. It is not for newcomers who have not learned probability before. This was just to sum it up for those who already have some background to it, and we will later solve problems on it, which will be more interesting than reviewing the theory, which was just supposed to be a review. So that is where I will end this video. Yep. Let's